Now, let's look at another question where we need to predict the gate rank of a student based on their performance in Big Tech and in gate mock tests. Let's assume there are three mock tests to consider. So, just like the previous question, our label is the gate rank itself. So, let's copy those values from the previous slide itself. It's 50, 200, 130 for S1, S2 and S3. Yes, 50, 200, 130, correct. But each input which corresponds to a student now is represented as a list of 4 different features. The BTech performance forms the first feature. Let me fill the percentage values from the previous slide itself. And that would be 80, 93 and 88%. However, we have 3 new features. Mock exam 1 is the second feature, mock exam 2 is the third feature, and mock exam 3 is the fourth feature. So let's put some arbitrary numbers for the time being, something like say 77, 63, 2, 55, 87, 24, 93, 11, 45. In the previous problem, we saw that a student was represented using exactly one feature. It could have been the CGPA or the percentage, but it was exactly one feature as the input and we have to map it to the target variable. Now, in this problem, we are representing a student as a collection of 4 different features, which makes the representation richer. And we are still finding the mapping of this representation with the target variable, which is the gate rank. So for the combined representation, I have to find the mapping. Yeah. So without really getting into the technical nuances, which we will later cover in detail, we can informally say that an input can be represented as a vector, where a vector is a list of n values, which makes it a vector of n dimensions. So input represented as a vector of n dimensions. In our previous problem, we have 4 features, so n is equal to 4. So each student is represented as a vector of 4 dimensions and is represented as follows. Let's say for S1 we have 80%, 77, 63 and 92. So this is a vector that represents student S1 with 4 different values, and they correspond to the label, or they have to be mapped to the target variable, which in this case is 50. So this forms the input representation. Now let's look at a classic example that is quite popular and is present in some of the standard textbooks. So here we need to predict whether a given day is a good day to play tennis or not. Here again, we represent a day as a vector of four features, namely outlook, temperature, humidity, wind. And this is the label that tells whether we need to play tennis on that day or not. So if you look here, outlook has three possible values, which is sunny, overcast, and rain. Temperature also have three possible values: hot, mild, and cool. Similarly for other features as well. Here each row represents a day with a unique ID given as the first column in the table. Each row is uniquely represented as a feature vector of 4 dimensions, 1 dimension for each feature. So if you again see D1, how will it be represented? It will be represented as sunny, hot, high, weak. And the label, so this is the input vector or the feature vector, and we should predict as no, which is the label. Yeah. Now let's get back to the first question we started off with. What do you think would form good features for this task? Should we include the lead role name? Should we include the second lead role's name? Should we include the, okay, maybe let me remove this. Let's not commit to anything, but let's say, yeah, should we include the lead role 1 name? Should we include the lead role 2 name? Should we include the director? Should we include the budget? So these are a bit subjective. We have to really think about the problem. So for instance, let's focus on this. Should we really include it or not? Should we include the first day's collection, fifth day's collection, or should we include the reviews? After all, we are predicting the overall collection. We have to predict the overall collection. So does it make sense to include the first days or the fifth days collection? Well, to answer that, we have to keep something in mind, that to whom are we designing this for, or to what purpose are we designing this for? For instance, we have to keep in mind that these features need to be available for a new input, in this case an upcoming movie, during the prediction as well. So if you are building a machine learning model for a production house to help them whether to predict to produce a movie or not, so we are designing it to a production house to decide whether produce a movie or not. If that's the case, it's obvious that we will not have any reviews, we will not have any collection information, we may not even have the number of screens released or length of the movie. What we may have are probably a different set of features. So then we cannot include these features that I have crossed here. But let's say if we use, if you're building a model for an OTT platform, and they have very clearly said that they don't mind waiting for the first 10 days after the release of a movie to arrive at a decision, then naturally all these features can be considered, because we will have those available. So if you are talking about OTT platform, wait till 10 days after release to acquire a movie too, then it's all right. We can include those. So the only thing to keep in mind here would be that we should only include those information as features which we can obtain during prediction. Include only those information which we can obtain during prediction as features. Now, since we know what are features and what are feature vectors, now let's cover the concept of dimensionality reduction. Several data domains involve huge number of features. So many a times a single data point needs to be represented using millions of features. In such cases, it makes sense to reduce the number of dimensions without really losing important and relevant information. So reduce dimensions as long as no valuable information is lost. So if we consider several domains, they contain huge number of features. For instance, if you look at a document or a book, it may contain thousands or even lakhs of words. Similarly, an image may contain millions of pixels. Now, why is this reduction important? So, high dimensionality, that means high number of features to represent an input, has many costs associated with it. Irrelevant features may degrade performance of some algorithm. It will be difficult to interpret and visualize this data. The computation may become infeasible because you need a lot of hardware, and there can be a hardware bottleneck that cannot efficiently or effectively capture all the data that we want to represent. And finally, there can be the curse of dimensionality. So what is curse of dimensionality? Again, informally we can say that as the dimensionality increases, the volume of our feature space increases so fast that the available data becomes sparse. So as a rule of thumb, again, if we have say 1000 features and if we only have say 10 or 100 data points, we may not even have enough data to tell that which features led to what kind of decision. So this is an important point to consider. So there is typically, due to curse of dimensionality, there is typically insufficient training data to properly train a model. However, we observe that we may compress the high dimensional space of features and bring it to a subspace. We try to find a subspace that best represents the data and then learn a model efficiently on this low dimensional subspace. So a book or a document may be represented using a feature vector of lakhs of dimensions, as it may contain lakhs of words. However, if we can represent the same book with a vector of a few thousand or even a few hundred dimensions, then it becomes more efficient to learn using it. So something that is lakhs of dimensions can we reduce it to few thousands of dimensions. The main part here to keep in mind is that we have to be mindful that there is no valuable information is lost. So principal component analysis, or in short form PCA, is a popular approach for dimensionality reduction. So in this lecture, we looked into an overview of dimensionality reduction. We conclude the introductory content on machine learning, which is this week's content. From next week, we will start looking into various aspects of machine learning in detail. Thanks.